Okay, wish you a very warm welcome to another session. Allow me to share my screen. Can you see my screen?
Yeah.
Yeah. All right, we'll continue from where we left. But what we're also going to do is, before we move to multivariate calculus, we'll do something a little bit more fun. So after the previous session, when Godwin is not around, he called me and he asked me a very interesting question. He said, look, whatever little that I have seen when it comes to the approximation. So for example, if you take, sorry, give me a moment. How do I, yeah. He said, I have seen this a lot. I have seen how DF is an approximation to this height, and most explanations have stopped there. Nobody quite talks about how do we actually move from this point to say this point, because every explanation stops at drawing the straight line at one point. Nobody really talks about drawing multiple straight lines or basically multiple tangents to reach from point A to point B. So what I thought was, we'll start this session with an example. I like doing things on Excel because I'm not a coder. So Excel is easy for people like me. So what we're going to do here is, I'm going to pick a function. In this case, y is equal to x to the power of 4. And I'm going to move from point x is equal to 3 to x is equal to 2. All right. And I'm going to use the gradient descent algorithm to do so. All right. So let's understand how we go about doing it. The good thing about Excel is it's easy to understand. You don't need to have any coding background to do so. So hopefully you should be able to appreciate what I'm doing here. And I also throw some nuances. There is some interesting stuff coming up. Okay. So what I've done is this. So we start with the first iteration. I have an x. I start with 3. So evidently, I'm going to ask questions. Otherwise, you guys are going to doze off. So what's the y value that I would start with? Anyone? You can probably see that on the screen, but I want somebody to answer.
3x.
Sorry, say that again.
3x cube.
No, the y value.
Oh, 81 it is here.
81,
Like,
correct? So it's x power 4, correct? I'll start there, right? So y value is 81, x power 4. Then going back to our basic formula, this is what are we trying to do? We are trying to, essentially we're starting from x equal to 3 to x equal to 2, but with small steps where dx is -1, right? That's what we're trying to do here. So I'm calling dx the learning rate because that's the terminology that we use in the machine learning world. So I'm calling dx the learning rate. And we know that df, which is a change in y, is nothing but f dashed of x multiplied by dx, right? So what is f dashed of x? If y is equal to x power 4. What is f dash of x?
4x cube.
4x cube. Why? X to the power of n. When you take the derivative, it's nx to the power of n minus 1. Okay. All right. So f dash of x is 4x cube. So I start at this point where x equal to 3. I figure out f dash of x. Okay. Let's go to this again. We know what is df. What is df? F dash of x multiplied by dx. So I have a learning rate. I'll come to the revised x a little later. F dash of x multiplied by dx is basically the product of 108 multiplied by negative 0.01. Okay. Now we know that. And by the way, what I started at x equal to 3. If my learning rate is negative 0.01, what is the point in, what x do I reach now? What is the value of x that I reach now? Anyone?
You move downwards, essentially.
Yeah, by what?
Towards negative.
Yeah, what's the value? Yeah, x.
Dx.
That's right. Or if dx is negative, then x plus dx, correct?
Right.
So don't you see I've reached 2.99? Would you agree? I started at 3. I have reached 2.99 when it comes to x. When it comes to y, I started at 81. I have f dash x multiplied by dx, which is negative 1.08. What do I do? If you look at this formula, it's simple. F of x plus df, correct? Here is f of x, which is y, plus df, which is nothing but f dash of x multiplied by dx. So here is y. So if you look at this formula, f2, it's 81 plus in bracket negative 1.08. Okay, so that's 79.2. Now tell me, I don't want the actual answer, but according to my straight line estimate, I am at 79.92, right? If instead of using the straight line, if I had traversed or moved down the curve, where would I be? Here I've taken the straight line route, but instead of taking the straight line, so going back to this example, of course, here we are moving in, we're moving up the curve. What you're seeing here, 79.92, is this point here. Of course, I'm talking in the reverse direction because here we are moving up the curve. So just pardon me for that. But this is assuming that I'm moving on the straight line, this is where I am. My question is, let's say I haven't taken the straight line route. Instead, I had moved along the curve. Where would I be?
79.9253.
No, that's right. But give me the expression that will help me calculate that. I don't want the exact number. Give me that expression. Would you agree that it's 2.99 whole to the power of 4? Why? Because I have already moved from 3 to 2.99. X is now 2.99. Had I stuck to the curve, y would have been 2.99 whole power 4. Would you agree, folks? So actual y. So when I say actual y, I'm basically assuming that I've stuck to that curve is 2.99 whole to the power of 4. So here is the calculated, or think of this as estimated y. I'm calling it calculated. You can call that estimated. Here is the actual. And what am I doing? I'm calculating the percentage difference. Why? This tells me how far is my estimated number compared to the actual number. Gives me a sense of the error. Okay, how good is my estimation? If I were to use this gradient descent algorithm. So in this particular case, the error is, how do I calculate error? It's simple. Calculated minus actual by actual multiplied by 100%. Okay, you don't see a multiplied by 100% because in Excel, I've designated this column as percentage. When you do that, it automatically multiplies it by 100. So you don't need to multiply it by 100 in the cell. Okay, so this is negative 0.006. Now let's look at the next step. What am I doing? Now let's understand this. I have decided to move along the straight lines. The whole idea of gradient descent algorithm is I have ditched the curve completely. I'm going to move along the straight line. So in iteration 2, the y that I start with, don't forget, is the y that I end with in the previous step. Do you see that? Look at this. Calculated y is 79.92. And here the y is 79.92. It is not 79.925. Why? Because what does 79.925 means? It means I'm on the curve, isn't it? All these points are on the curve. I am not on the curve anymore now. I have ditched the curve completely. I'm basically looking at straight lines now. So
This is a question.
Yep.
See, so now when you say actual y, that is on curve, right? It may be or may not be, right? Because you see, the curve is like this, and we are actually moving on towards x, either incrementing that or either decrementing that. Okay, so the curve can be anywhere, or sometimes when we are actually incrementing our learning rate, we may by default itself we can come out of the curve also, right?
Yes, we are. Yes, you're right. The actual y is the curve, isn't it? Well, it's basically, if you look at the actual y, so when I use the word actual, assuming that this is the x.
See, the actual y we are actually taking because we have a function y is equal to x to the power of 4. So
That's
whatever, if for every value of x, there is another value of y.
Correct.
So this is the function. So based on that, we are actually going to.
That's right. That's right. But then the fact is we are using a straight line to estimate, isn't it? So the calculated y is our estimated number. Actual y is, because how do we even know that we're doing the right estimate? You need an actual number for the purpose of comparison, which is why I've also jotted down the actual value. All right.
Okay.
Now, my point is that the key thing that you need to understand is when we move to the second iteration, and when it comes to y, what is that y? Is that the actual value at the end of the previous step, or is it the estimated value at the end of the previous step? The point that I'm trying to make here is, and let that be very, very clear, that it is not the actual value at the end of the previous step, but the estimated value. Why? Let's understand when we run this algorithm, just imagine that this column doesn't exist at all. The reason why I put that column is purely for comparison. From an algorithmic standpoint, this column doesn't exist at all, right? So what is available to the algorithm is only column H. So at the end of step 1, I am at y 79.92, and that's my starting point in step 2, in iteration 2. Now, x is 2.99. Why 2.99? Because I ended with 2.99 in the previous step. Then, but I know the derivative. Derivative is a standard formula. It is 4x cubed, correct? So if x is 2.99 now, I can calculate the derivative now, 4x cubed, right? Again, learning rate is negative 0.01. This is my revised x. I again do an f dash x multiplied by dx. I get a calculated y. And now I have an actual y again. Because again, let me reiterate, the purpose of populating actual y is just to do comparisons. Okay. Then I again figure out what is my error. Now I do this for 100 iterations so that I reach x equal to 3 to x equal to 2. That's the whole objective. So I start at x equal to 3. I eventually move to x equal to 2. And I wish to see how far am I from the actual y. I'm about 2.44% off. So that's the deviation, right? So the idea is this. At every stage, remember folks, initially the error is less because I just started the approximation. But then don't forget, as I keep proceeding, I'm building on top of approximation on approximation on approximation, right? Because remember, I don't have the y. I only have a calculated y with me. So it's like when I move to step 2, I'm already using an approximated value. When I move to step 3, it's an approximated value of the approximated value that I'm going to use in step 3. So eventually, when I literally move to step 100, I've done so many approximations, linear approximations, and as a result, negative 2.44 is the error. All right. Now let's do another thing now. I'll run the same algorithm. Nothing changes. Okay. Nothing changes. Now what I'll do now is I'll just change the learning rate. That's the only change here. So instead of keeping the learning rate as negative 0.01, I decrease the learning rate, or rather, I mean, when I say decrease, I mean the magnitude is decreased, okay? But sign wise, it's an increase. So don't get confused about that. But I'm decreasing the magnitude so that I move only a little backwards. I say backward because the learning rate is negative, okay? Now, it's a question for this audience. So if I have to move from x equal to 3 to x equal to 2, and if my learning rate, I'm keeping it constant, okay, to make life easy for us. And if my learning rate is negative 0.001, can anyone tell me how many steps do I need to take to reach from 3 to 2? 1,000, right? Why? Because from 3 to 2, the difference is 1. I move in steps of, I mean, the size of each step is 0.001. So of course, I need to take 1,000 steps. So here we go. So I again start calculating the error in percentage. So let's do a comparison now.
We see what is the how do you calculate the error?
I'll show you. I'll show you. Yeah. So the error is computed as calculated y minus the actual y divided by actual y into 100%. How much have I deviated from the actual in percentage terms?
So in the algorithm, we use this error?
No, of course not. We don't.
Oh, only for our
you might use it in training, for instance.
Okay.
You may want to. Right?
In the training part.
Okay. Yeah, in the training part, you may want to use this. It may be useful, all right? So that you know how far you have deviated. Okay. No, but again, the objective there is to figure out the cost function. So you can't even use this. I mean, the objective there is, sorry, not to figure out a cost function. It is to minimize the cost function. Okay. So you can't even use this there. Okay. The objective, okay, let me put it this way. This is not exactly how the algorithm works. The algorithm will never have column T. But what we are trying to showcase here is, assuming that I'm using that algorithm, how far am I from the case where, assuming I have the actual values with me, how far am I from that? That's what I'm trying to demonstrate here. Okay. So here we go. So if you look at this, so here I reached this point and the error was negative 2.44%, right? So you see the error here? I reached the same point, which means x is equal to 2, but the error now is negative 0.238%. So by increasing the number of steps, or rather by increasing the number of iterations, and by decreasing the absolute value of the learning rate to make, if I keep it very, very small, I can ensure that my error is much less, right? Because if you look at this case, the error was negative 2.44. I reached the same point. If you look at it, x is still 2 here. But then the error that I see is negative 2.44%. But then if the learning rate were to be 0.001, negative 0.001, then the error that I see is much smaller. negative 0.238. Okay. Now let's do one more thing.
We see a question here. See.
Yep.
So in the first one, right, where the learning rate is, I mean, the first case, you have less number of points, but still the linear approximation. You mentioned, right, it's a linear approximation of approximation, but the error is high. In the second case, you have more data points, but still the error is less.
Yeah, that's because, yeah, I'll tell you why. That's because look at this. Look at this. If dx is very, very small, let's say dx is this, don't you see that I will be still on this? My curve and the line would exactly be the same almost. You see, take this case. If dx is very small, I'm here. Again, I'll draw another tangent there. Dx will be very small. I'll be very close to the curve. Then I'll draw another tangent. Dx will be very small. I'll still be close to the curve. Let's say I'm here. I'll draw another tangent like that. But then dx will still be small. I'll be close to the curve. The problem crops up when dx is huge. Because then, look at this. If dx is huge, I'm already here. Right? I'm so far away from this guy. And then, if I try to draw a tangent, I'll get a line something like that, which is parallel to this point. Right? So I'll get a line something like that. But I've already started moving far away, isn't it? So which is why when you start, see, if you look at one trend, I'll show you a trend. I'll always start with a low error. Look at the initial error. It's negative whatever, 0.0000 whatever. And if I go all the way down, it has increased. That trend stays. That doesn't change. I start with a small error, but the error keeps increasing. Why? Because with every single step, I'm doing an approximation of an approximation, approximation of an approximation. So error will keep increasing. So that doesn't change. But given that my learning rate is much smaller as compared to what it was earlier, certainly the error rate, certainly the error in this case is much higher. Right? Now, did I answer your question?
Yes, we see. It's clear.
All right.
Yeah.
Now I'm going to do one more function. X to the power of 8. Okay. So here's a different function, x to the power of 8, and I'm moving from x equal to 3 to x equal to 2. Now, anybody, what is the first derivative of x to the power of 8?
8x power
8x power 7. That's right. So that's the only change here. Otherwise, everything else remains the same. Nothing changes. It's just that this derivative changes. All right. Now let's look at this. I'm going to replicate this 100 iterations. Learning rate is going to be negative 0.01. It's just that I changed the function from x equal to y equal to x power 4 to y equal to x power 8. Now just look at the error. By the time I reach 100 iterations, it's negative 33%. Right? Now, I did the same thing here. This time, 1000 iterations. This is negative 3.232%. Okay. Much better than negative 33%. But if you compare it with the error that we saw here, it's still huge. You see, it's negative 0.23. Here it is negative 3.23. So, okay, so forget this for the moment. Let's just compare this. I start from 3, move to 2. The function is x power 4. I start from 3, move to 2. The function is x power 8. In one case, after 100 iterations, I see negative 2.44% error. 100 iterations here, I see negative 33%. What is happening? Why? Anyone?
because exponentially it changes very quickly compared to the one on the previous function.
It's not an exponential function here in a way,
Okay.
but you're right. What is happening here is you will find x to the power of 8 is more curved as compared to x to the power of 4. The curvature of x to the power of 8 is much more, which means, just imagine, folks, I'll tell you how x to the power of 8 will probably look. Just look at the pointer. It'll probably look something like this. That's how x to the power of 8 will look. So the point that I'm trying to make here is, if I move a little bit, some dx here, when I deal with x to the power of 4, the curvature is much less as compared to x to the power of 8, which is why what you find is, for the same learning rate, the error, and I mean, for the same learning rate, and assuming that I'm moving from x equal to 3 to x equal to 2, the error percentage for this function, which is y is equal to x to the power of 4, is much less compared to the function y is equal to x to the power of 8. Okay. Now, this is the reality. Now, how do we solve this problem? So what we'll do is, we'll go one step further. So again, in class 12, we would have touched upon it. I'm sure everybody would have heard of this in engineering. So one Mr. Taylor came up with a series called as Taylor's series, where, so if you look at a function, what you are seeing, this is called as a first order approximation of the function. Because if you look at this symbol, it's an approximation. You see that? They don't put an equal to here. This symbol essentially means it's approximately equal to. Now, what we're trying to do here is, this gap, don't you see the gap is because of the curvature? Right? It's because of the fact that this is curved, you have that gap. If you bring another curve which is far too curved, then the gap will increase. So the question is there a way to bridge that gap? At least somewhat. And that's why Mr. Taylor came into picture. And what he did was, he did the following. It's a long series, by the way. Okay, so typical Taylor series will have infinite number of terms. But of course, our objective is not to get to an exact number, it is to get an approximate number. So what we'll do is, if you look at Taylor series, it says f of x plus dx, where dx is very small, approximates to f of x plus f dash of x multiplied by dx. We understand this portion really well because this is what we've been doing so far. Then you add another term, which is this 0.5 multiplied by f double dashed of x into dx the whole square. Now, question, what is f double dashed of x? What does it mean? Anyone?
Second order
Second
derivative.
derivative.
That's right, second derivative. Okay. So what we're doing here is, we're saying, look, f of x plus dx, the first approximation we started with, which is f of x plus f dash of x multiplied by dx, is a starting point. You can improvise on top of that. Okay. And this is the improvisation. 0.5 multiplied by f double dash of x multiplied by dx the whole square. Okay. That's what Taylor series suggests. Now let's see what happens if we apply the Taylor series to our problem. Okay. Here we go. Univariate, second order. So we'll do this. The crazy one where we saw 33% error. Okay, I'm not going to show you this. This is easy. But let's do the one which which kind of stumped us, where we saw 33% error. So what are we doing here? We're doing this exactly the same thing. The only difference is we are adding f double dashed of x. So if f dashed of x, which is the first derivative, is 8x to the power of 7, can anyone tell me what is the second derivative of 8x to the, what is the second derivative?
56
56 power x to the power
6 powers.
That's right, correct. 56 to the power x to the power of 6. All right. So here is f dashed of x, here is f double dashed of x. Learning rate remains same, revised x remains same. Here is f dashed of x multiplied by dx. This is stuff that we did before. The only thing that I'm doing now, which is different, is I've added this term now, 0.5 multiplied by f double dashed of x multiplied by dx square. Okay, comes from Taylor series, this bit. Okay. What is the calculated value now? It's just nothing but f of x plus f double dashed of x multiplied by dx plus 0.5, I'm sorry, let me repeat it. F of x plus f dash of x dx plus 0.5 multiplied by f double dash of x into dx squared. So this summation, I'm doing it here. All right. 3 terms, actual, error. No difference as compared to what we did before. The only difference is I've added this term. Okay. Now let's look at what we have. Look at the error, folks. 0.25. Same number of iterations. I haven't changed the number of iterations. Right? What we saw here when we stopped at the first order of the Taylor series was we saw an error of negative 33.68. And here you see an error of 0.25%. That's the kind of difference that you see when you introduce a second order approximation. Before I proceed, any questions?
So in Taylor series, the more the terms, the less the error will be. That is the observation.
Exactly. Absolutely. Correct. So the thing is, the more the terms, the lesser the error. The smaller the dx, the better the approximation. Both ways. So Taylor series will not work if dx is, say, the same thing. If dx were to, if the learning rate were to be, say, instead of negative 0.01, if it were to be, say, negative 0.1, then it won't do that well. So dx has to be small, and you also need to ensure that, at least in Taylor series terms, the more terms, the better it is for you. But in reality, we stop at 2. Nobody goes beyond 2. Extensively used in finance. This first order and second order is extensively used in finance to figure out the value of certain instruments, not stocks, but there's something called as bonds, and Taylor series is extensively used to figure out the value. Okay. Now, any further questions on this, at least?
We see it is so it is like if you have so when should we go with this second order? Is it
brilliant question. It's safe to do both, right? But just look at it this way. Just think about it, okay? If you take this case, okay, y equal to x to the power of 8. I could have opted for the first order, and I could have opted for 1,000 iterations, right? Where do I reach? 3.23 after 1,000 iterations. And basically, let's say 1,000 calculations. Now here, I've stopped at 100. The number of calculations has effectively doubled. Why? Because I need to calculate this term now, correct?
Yes.
So that I can add it to the calculated value. So this term has to be calculated. So in terms of the number of calculations, it's not 100. If it was 100 before, it is 200 now, isn't it? Why? Because I'm adding 100 more calculations now, but my approximation is pretty good. So I would rather prefer doing this instead of keeping it, as a first order approximation and doing 1,000 iterations, right? Maybe again, if I increase rather decrease the learning rate to 0.0001, I might get a better approximation. But that means just to move from 3 to 2, I will have to, there'll be 10,000 iterations in that case, correct? So what I can do in probably 100 plus 100 calculations here, I will end up, doing about 10,000 calculations. So I think we'll have to weigh, which one is better. Clearly, to me, this looks to be better but again, it also depends on the function. I'll tell you why. I do first order, let's say. If the function is not very curvy, then the first order approximation is sufficient. Don't you think so? I'll do pretty decent. I don't need to needlessly compute a second order derivative, right? I'll get a pretty good approximation for my actual value if my curve is less curvy. So the more curvy it is better to move, it is better to introduce the second order approximation, right? I think that's one way to look at it. How curvy is your cost function? That's probably one way to figure out whether to move to second approximation or not. Does that answer your question?
Yeah, yes.
All right. Any further questions on this? All right. Okay. Now we go back. Let's move to the multivariate world. So when we say multivariate, what we mean? I'm going to keep it simple. Again, you folks, you need to understand what is domain and what is range. It's extremely important. So when we say z equal to f of x comma y, which means imagine x and y to be our independent variable and z to be the dependent variable. Naveen, I don't want you to answer. Yash, I don't want you to answer. Someone else. What is independent variable and what is dependent variable? Anyone in the audience?
Yeah, we see dependent variable is something which is derived from the independent variables.
Exactly.
So
Changes
whenever we
independent
change
and acceleration.
independent variables, then there is an impact on the dependent variable.
Exactly.
Yeah.
So independent variables are set by, we can set it. The values of the independent variables can be set by us. The dependent is driven by the values of the independent variable. Okay. So when we say z equal to f of x comma y, which means we set values for x and y, and depending on some function, we derive z or z. So z is the dependent variable, x and y are the independent variables. Now, x and y can take any value, correct? And that's called the domain. if you look at this x comma y, we would say it's a subset of R squared. What does that mean?
Two-dimensional X.
Correct. What is R there? What do we mean by R?
R is actually dimensions.
But what is exactly R?
Real numbers.
Space.
Yeah, it's a real number.
Real.
Okay. Remember, folks, R means a real number. What's a real number? Abhinav, I don't want you to answer, someone else. What's a real number? Square root of 3, is that a real number? Anyone?
Yeah.
Yes.
Okay. 2 times I. Is that a real number?
That is imaginary number.
That is imaginary. Correct. That's right. So your positive, your negative, your fractions, your irrational numbers. So put all the rational number and irrational number together and you get this nice little number line. That's the real number line. Okay. So X can be any number in the real number line. Y is also similar. It can be any number on the real number line. So X comma Y is a combination. You see that? I can pick root 3 as X and say root of 9,449 as Y. Any combination. So which is why we say it's an ordered pair. It's a subset of the real plane R square, which means, why do we say subset? Typically, we would operate with a smaller set, correct? We're not going to allow X and Y to be any value. There will be some set, some subset of all the possibilities of real numbers. You know, that's how it will work in practice. So that's the domain. And then there is a function which maps this domain to, now can you tell me, is Z on R square, is Z on R cube, or is Z on R?
R.
R, exactly. That's the whole deal there. Why? Because we are saying, now, yes, there are two variables here, but eventually what the function is going to do is it is going to map to only one number. That one number will be some number on the real line. We don't know what number it is, but it will be some number on the real line. It could be root 3, it could be 0, it could be negative 75, it could be 10,25,002. That's perfectly fine. But it will be only one number. So which is why Z would lie on the real line. It's R. Okay. So the range of F is a set of all real numbers. Is that clear? Now, how do we plot it? No big deal. Geometrical visualization. Again, folks, I keep insisting geometry is nice, but don't get caught in geometry. Okay, useful for visualization, nothing more. So here is X, here is Y, here is Z. Anybody here? How do we decide? What is the convention to decide what is X, what is Y, what is Z?
The most dependent variable become X.
No, not necessary. No, if you look at this graph, why didn't I say this is X, that is Y, this is Z? What is the convention? Anyone? Abhinav, I don't want you to answer. Let's see if others have something to say. What is the convention?
Z-axis is always perpendicular to the plane created by X and Y axis.
Okay, so does that mean I can point Z down? Can I?
I'm not sure about that.
Can the positive Z be down? Abhinav. Now let me ask Abhinav. What do you think, Abhinav?
Actually, it's in some clockwise arrangement. X, Y, and Z should be. X should be to the clockwise.
Okay. Let me tell you how it is. There's something called as a right hand rule.
Yeah, that's what.
So if you had learned physics in class 11, 12, so there used to be a law called as Biot-Savart law. Okay. So when you have a current, in a magnetic field. And if you want to determine the force acting on that piece of wire, so you follow, the force acting is calculated using the Biot-Savart law. All right. So it is something like IDL cross B. So you do a cross product there. So how do you determine this? The idea is simple. Just your fingers move in the direction of positive X. Okay. Fold your fingers like that. That's positive Y. And this is positive Z. That's it. So keep your fingers in the direction of X, fold it towards Y, you will get positive Z. In this case, keep your fingers in the direction of X, fold it towards Y, your thumb should point towards the positive Z. This is the convention, standard convention, always. Okay. So what do we do here? It's simple. You have X, you have Y, you have Z, which is a function of X and Y. Okay. No big deal. That's one point. Of course, you would want to change the X and Y values to see the various values of Z. So what would you get? What is this called? The one to the right. Is that a line? What's that? Abhinav.
Plane.
Is that a plane?
What were you asking? The shape
does that look like a plane?
No.
What's a better word? Plane means it's flat, right?
So
sorry?
Some surface.
Is it
surface? No, it's surface. It's some surface, correct? You don't know what surface it is. It could be, for example, even spherical. Who knows? It could be it could be a plane, but whatever. But it's some surface, right? So you have X, you have Y, you have Z. So you vary your X, you vary your Y. Of course, you'll get various values of Z. So you plot your Z. And what you get is a surface. Okay, that's how you visualize functions of two variables. Okay. Now, we'll take an example. We'll take it from the machine learning world. Allow me to thank Kayal Vidi for giving me this nice looking surface. So let's take an example. I'll read the story here so that you understand the context. The context is the following. So let's assume a bunch of points, x1, y1, x2, y2. x1, x2 are independent variables. y1, y2 are target variables or dependent variables. We're looking to build a linear regression model that predicts y based on the following equation. What is the equation? Y is equal to W0 plus W1 times X. Now, we are using what is called as a stochastic gradient descent. Now, the difference between gradient descent and stochastic gradient descent is when we use stochastic gradient descent, the cost function is determined based on one data point, period. Okay. When we do gradient descent, the cost function is determined based on all data points. That's the only difference between stochastic and the traditional gradient descent, or what is called as a batch gradient descent. So let's say we're doing stochastic gradient descent. And what are we doing? We are focusing on one data point. Let's say that data point is 2, 11.88210183. That's the point. So this is the X, this is the Y. Okay. Now, how do we determine the cost function? It's simple. Actual value of target variable minus expected value, the whole squared. That's the cost function. So what's the actual value of the target variable? Anyone? Abhinav, I don't want you to answer. Yasholeka, no. Naveen, no. Someone else. I want somebody new to answer. Somebody who hasn't answered today. Not Pavitra. Anyone else?
The value that is 11.8821.
Exactly. Okay. Mugundan, right?
Yes.
Right. Okay. So that's your. So the actual value of the target variable is 11.88210183. Okay. Now, can somebody tell me what is the expected value? Not Mugundan, someone else.
W0 plus W1X.
Okay. So what is the X value here?
2.
This data point.
2.
2. Correct. So the cost function, don't you see, it's this 11.8821 minus W0 plus 2 times W1, the whole square. Okay. That's our cost function. Now we're going to plot this. So here is that plot. The one to the left is the plot. Okay. So here is an example of how a function of two variables will look like. Of course, in this case, it's very interesting. In this function, what are the independent variables here? Can anybody tell me? Not Rakesh, not the usual suspects. Someone else. In this function, what are the independent variables?
W0 and W1.
That is right. Correct. Of course, I shouldn't have asked you. You would know the answer. You're right. W0 and W1 are independent. Okay. Someone else. Why are they independent?
Because we can play with the
Hey,
value.
no. Like, come on, Pavi. You shouldn't be answer.
Sorry,
Someone
yeah,
else. Why are W0 and W1 the independent variables? Come on, folks. There are 29 people on this call, including me. At least 20 haven't answered.
Because it is not dependent on anything. You can assign any value.
Correct. You can vary W0 and W1. You see that? I can play around with W0 and W1. Correct? What is the dependent variable? Sanjay, I don't want you to answer. You're the one who answered, right?
Yeah.
Okay, someone else. What is the dependent variable here? Anyone? Okay, I'm going to pinpoint people now. Jaren, you caught my attention.
Is that Y?
Where is Y? This is the equation. Here's the equation. Here is a graph, or rather the surface. My question is, what is the dependent variable? The independent variable, Sanjay said it's W0 and W1. So what's dependent here?
Cost function.
Exactly. The cost, essentially, correct? I don't want to use the word function. The cost is the dependent variable. Why? The cost is dependent on W0 and W1, correct? So,
Yes.
So here we go. So what we have done here is, this is an example from our ML world. Kind of helps us understand how we would visualize functions of two variables from the ML world. So cost function, where you work with linear regression in just two variables, W0 and W1, you get a cost function, something like this, which you can visualize using a surface, like the way we've done it here. All right. That's just an example. Now let's move to the idea of partial derivative. Now we are working with multiple independent variables. I think we all understand what independent variable means. At least in our context now, we have two independent variables that we are working with, X and Y. There's a Z, of course. But in reality, you'll work with a lot of independent variables, right? Not just two. So the whole idea of the partial derivative is, think of all those independent variables as knobs. So we've all played around with, this is of course old school, but we've all played around with media player, where you have all those stuff moving up and down that you can move up and down. You pick one, you play around with it and see the impact of the movement on the audio output. Then you play around with something else, right? So that's something that we always do. So think of partial derivative as one where when you have such a complex function, in this case, a function based on two independent variables, What we're trying to do here is we keep everything else constant. We don't play around with them. Just take one variable, try to change the value of that variable and see the impact of that change on the dependent variable. That's the whole idea behind partial derivatives. Okay. So if don't get perturbed by this equation, it's very simple. Let me explain that. But before that, I'll briefly read this sentence for you. Let f of xy be a function of two variables. We understand that x and y are the independent variables. Then we can say that the partial derivative of f with respect to x, written as dou f by dou x, or f subscript x, is defined as, what do we do here? We don't change y. We keep y as is. So if you look at it, y remains the same. So initially I start with f of x comma y. I don't change y. I just change x by a small h. And of course, how do we calculate derivatives? The change divided by, just go back to how we calculated derivatives for functions with one variable. F of x plus delta x minus f of x by delta x, as delta x tends to 0. I think, of course, the limit, something that we all learned from class 11, class 12. This is very similar. You keep y constant, change x by a small amount. Maybe we could have called this delta h instead of h, but it's okay. It doesn't really matter. So this expression gives us the partial derivative of f with respect to x. Similarly, we can figure out the partial derivative of f with respect to y. Very, very similar. What do we do? Keep x constant, change y. That's it. Okay. Now, in the world where, let's talk of the one variable world. Let's say there's a function 3x squared. 3x squared. What is the derivative of 3x squared? Anyone?
6x.
6x. That's right. So how do you treat 3? X square, we know, it's very simple. Constant. So whenever you're dealing with constants and you're multiplying constants with a variable, you take the constant out, just calculate the derivative of the expression where you find the variable and then multiply them, correct? 3 plus x square. Yash, I don't want you to answer, someone else. 3 plus x square. What is the derivative?
2x.
0 plus 2x.
Sorry, was that Arun?
Rakesh, 0 plus 2x. So
0 plus 2x. Okay. So when constants are, it's part of the additive process, then of course what happens? The derivative of constant is 0. Okay. So let's understand that. Now this principle we can comfortably use when we are calculating partial derivatives. As I said, remember, while calculating partial derivative, when you're calculating with respect to x, you treat y as a constant. When you're calculating a partial derivative with respect to, say, y, you keep x as a constant. All right. So just remember your basic univariate calculus. Apply the same principles, it will work. Now, I don't want the usual suspects, but I want someone to help me calculate the partial derivative of this function with respect to x. Someone. Not the usual suspects, someone. And I don't want Jaren to answer, someone else. Not the Mugundans of the world, not the Aruns, someone else.
It is 2x.
Now, who is this? Who is this? Please.
Separation.
Go ahead.
Yeah, it is 2x minus 3.
Partial
And,
derivative of f with respect to x.
Okay, so it is 2x minus 3y, then minus 4.
Okay, no. Help me with each expression so that people understand. Okay. So the first is 2x.
So
Okay.
first is x square. So that will be like 2x.
Okay.
Okay. And in minus 3xy, since we are considering y as constant, so minus 3y will be constant and x will be derivative of x will be 1. So it is just minus 3y.
Correct.
Then we have 2y square. Since y we are treating as constant, so its whole term is constant. So it will be 0.
Correct.
Then we have minus 4x. So derivative of x is 1. So it is minus 4. And plus 5y. 5y we are treating as constant, so 0. Minus 12 is constant, so it is 0.
Perfect. Anyone who hasn't understood this so far? Okay. Someone, of course, apart from subrogation, dou f by dou y. Dou f by dou y. Who can you just? I don't know who's talking, so can you please? Go ahead, Madhumita. Take it step by step, okay? Step by step. X square.
So x is constant here, so that term is 0. And it's minus 3xy. Again, x is a constant. So we'll leave it. It's 3x.
Minus 3x, right?
Yeah, minus 3x plus derivative of 2y square is 4y.
Okay.
X is the constant, so that 4x term is 0.
Okay.
Plus derivative of y is 1 plus 5. And 12 is the constant, so 0.
Perfect. That's right. You're right. Okay. So we understand how to calculate partial derivatives. It's very easy. Once you understand your basic univariate derivative calculation, partial derivative calculation is very easy. Now, that's a question in your imagination. We'll come to that in a short while. Can we think of these partial derivatives as a vector? All right. Now, again, when we use vectors, right, there are so many interpretations of the word vector. The most basic interpretation of the word vector is it's an array of numbers put together. That's one way you can look at it, right? And there's a geometrical interpretation of vectors too. So in fact, you can actually think of partial derivatives as a vector from both perspectives. As an array of two numbers, and there is a very geometrical interpretation of this too. But again, I keep insisting, don't get caught in the tyranny of geometry. Why? Because it's a lot of fun to look at geometry, but it's not going to help you the moment you increase the number of dimensions. Okay, so don't get caught in the tyranny of geometry. Understand the intuition, understand the principle, understand what is happening, because when you move to higher dimensions, geometry is not going to help you, but the intuition that you get from geometry will help you a lot. Okay, so let's move to the next slide and see if we can make some sense of how to visualize partial derivatives. So if you look at this is a function, and here's a point, some crazy function. So you have x, you have y, and you have z. Somebody here, there are three colors here. So can somebody tell me? And I taught you a convention. Remember, folks, the right-hand convention. So which color denotes x, which color denotes y, and which color denotes z? Not Madhumita. No, this time I want someone else to answer that.
Is red X, green Y?
No, not Yash. Come on. Not the usual suspects. I want someone else to answer, Yash. Sandhya, you're quiet today. What happened?
Network bandwidth is low.
Okay, fine. Someone else then. What is silence supposed to mean? Somebody is attempting. Who's that? I'm going to keep silent. I'm going to stay mum.
Red is X, Y, green is Y, and blue is Z.
Who was that?
Vidya here.
Oh, perfect. You're
AI
right.
consultant.
Correct. That's right. Oh, AI consultant. That's right. Right. So idea is simple. Keep your fingers in the direction of X. Fold it towards Y. You should get Z. So she's right. Vidya is right. X is the red. Y is the green, and Z is, of course, the blue or violet or whatever I think it's blue, right? Okay. Now, let's look at how do we calculate from an intuition standpoint. Again, it's fun, folks, because we again go back to the tangent that we learned. All right. It's the same concepts. The univariate world, we learned tangents. It's the same tangents here. It's just that you're applying it in a different way. Nothing changes. So when we say the partial derivative of X, then don't you see that Y has to stay constant? Y shouldn't change. So which means, look at this. Look at my, I'm going to use my mouse to traverse a curve, and I'm going to ask a question while I traverse. Okay. So just watch my mouse traversing a curve like that. It's a curve, not a surface. Number one. What my mouse traversed was a curve, not a surface. I'll traverse again. Here is my mouse traversing a curve. Now, given that I've traversed this curve, can someone tell me, when I traversed this curve, what was constant? Was X constant or was Y constant? Not the usual suspects. I want someone else to answer. When I traverse this curve, I'll do it again for you folks. Here I go, here I go, here I go. Was just look at that whole image and tell me, was X constant or was Y constant? I didn't bring Z at all. Z, of course, changes. Who was that? Sandhya, is it?
Yes, VC.
That's right. Correct. Y is constant. Why? Okay, that's no pun intended, but yes. Y is constant, and that's because when you look at this, you see this is Y. This axis is Y. This axis is X. This axis is, of course, Z. So when I traverse this curve like that, of course, Z changes. There's no question at all. But then don't you see when I traverse it like that, X is also changing, right? Evidently. What hasn't changed is, look at this, the Y remains the same. Engineering drawing stuff, folks, first year engineering drawing, right? The way you visualize this, don't you see that the Y remains the same? All right. So, and that's what we want. What are we trying to do here? When we calculate the derivative, the partial derivative of this function with respect to X, we keep Y. And when we calculate this, we're calculating at this point. Let's be very clear. So here is a point where we want to calculate the partial derivative. We keep Y constant. So I've kept Y constant, and I move along that tangent line to figure out the derivative, right? So to do that, I change X and I move along that tangent line. So that's the direction of my partial derivative, dou F by dou X. Okay. Now, dou F by dou Y. Now let's understand this. And I'm again going to use my mouse and traverse a curve. Just follow me. Here we go, here we go, here we go, here we go. That's the curve. Not the usual suspects, somebody new. When we traverse this curve, What is constant? What
It's
doesn't change?
X-axis,
Who's that?
It's ministry.
Ministry. You're right. X doesn't change. Don't you see that? X remains the same. Y changes, and of course, Z changes, no doubt. So, and I can draw a tangent here like that. So let's combine both of them together. So you're basically drawing two tangents here. That's the whole idea, folks. In the univariate world, we were drawing one tangent. In the multivariate world, we'll be drawing multiple tangents, each pointing in different directions, right? So you have one tangent pointing in one direction, another one pointing in a different direction, which is why I say you can also visualize these as vectors, okay? Again, don't worry too much about it. We're not going to probe further, but it's just helpful to understand that we can look at these as vectors too, geometrical vectors too, okay? But don't worry too much about it. But I think it's useful just for visualizing. I'll stop here for any questions. Are there any? All right, wonderful. Now you might be wondering, what the hell is this? Higher order partial derivatives are. Okay, now you must be wondering, why the hell are we doing all this? Why are we moving to higher order partial derivatives? Remember, folks.
You see, question is like, why are we doing partial derivatives?
I'll come to that. I'll come to that. Because it's useful when we do approximations. Remember, folks, there's a very clear application that we're looking at. When we did univariate, we started, one of the key things that we were trying to do was linear approximation. Gradient descent, essentially, right? And of course, life was easy here because it was just one variable. Now, what happens if it's two variables? How do you solve this problem? That's where partial derivatives come into picture. Instead of the function being f of x, it's f of x comma y now. So how do we do gradient descent when I have two variables? How do I calculate? If you remember this from the Excel, I was lucky here. One variable, I calculated f dash of x. I did everything. Life was easy. But now my function looks a bit different. Let's say the function is x to the power of 4 plus y to the power of 4. How do I do gradient descent in that case? That's where partial derivative comes into picture.
Easy. So when you're doing the partial derivative, it is like doing it 2 times univariate, right? That is what it looks like.
Exactly. Correct. That's one way to look at it.
But in the real world scenarios, right? This is that particular, that means the dependent variable will be influenced by only when these both are actually acting, right?
Correct. That's right. That's right. So they combine together. So effectively what happens is, the way we are doing this is,
where we are considering that combined impact on that.
Correct. We will.
Okay.
So when we do partial derivatives, effectively, when we do linear approximations for two variables, you're right. We'll take one variable, another variable, then combine them together. Okay. All right. Now, the thing is, coming back to higher order partial derivatives, why do we need it? Remember, folks, I'm going back to the linear approximation case that we started with. Why did we need f double dash of x? Anyone? Remember, the whole session started from...
To get more precision.
Exactly.
More curvy.
Yes, more curvy. Don't you think, just as in the univariate world, things can be curvy, why can't things be curvy in the multivariate world? That's possible too, right? Curvy stuff is there in every single world. It's not something that is there only in the univariate world. I can have a very complex function, x to the power of 8 plus y to the power of 8. That will be very, very curvy, right? So that's where higher order partial derivatives will be useful. Okay. Now the question is, if there are two variables x comma y, how many higher order partial derivatives will be there? Anybody? X comma y. And when I say higher order, I mean, let's just focus on order 2. I'm not talking of 3, 4, 5, etc. Just order 2. How many will be there?
4.
4, exactly. Why? Because first is very simple. Dou f by dou x, dou f by dou y. Okay, that's very simple. Order 1. Now I can do the following combinations. I can do dou f by dou x first, and then I can do a partial derivative with respect to x or a partial derivative with respect to y, correct? And the same thing I can do for dou f by dou y. You see that? So I'll have 4 combinations now. So just look at this part. So I essentially have 4 different combinations for partial derivatives of order 2. All right. So the way we represent that is, for convenience, you either call that as dou square f by dou x square. That means you've already taken dou f by dou x and you do another partial derivative on top of that. This is dou square f by dou x dou y. What does it mean? It means I first figure out dou f by dou y and then I do another partial derivative on x. Then this is dou f by dou x. That's the first step. Then I do a partial derivative on y. And finally, this is dou square f by dou y square, which means I calculate dou f by dou y. I'm sorry, I calculate derivative of dou f with respect to y, partial derivative, of course, and I calculate another partial derivative on top of that with respect to y. Okay. In the partial derivative world, this is represented as fxx, fyx, fxy, and fyy. That's how you represent it. Okay. Now here it is, folks. I won't go to the second order. We'll do it in the next class. But let me just stop with linear approximation. Okay. We know how we did linear approximation in the univariate world. How did we do it? This is how we did it. F of x plus dx approximates to f of x plus df, where df is f dash of x times dx, right? Simple. We take that as inspiration and we go to the multivariate world. In this case, 2 variables. So how do you calculate f of x plus dx comma y plus dy? It is nothing but f of xy. It's something like this. But now the df comes in 2 parts because we have 2 variables. So we do dou f by dou x, the partial derivative of x multiplied by dx, plus partial derivative of y multiplied by dy. That's it. That's your linear approximation. Okay. Now, I'll just take one example and I'll stop with that. Gradient descent. I'm not going to go through a lot of details. We go through the detail in the next class, but briefly, I'll tell you what we're doing here. Okay. What we're doing is I take a function x power 4 plus y power 4. I start from 3. I move over to 2. So essentially what I'm doing is I'm trying to replicate this formula here. F of x comma y plus dou f by dou x into dx plus dou f by dou y into dy. All right. So if you think about it, it is no different from what we did earlier. The only difference now is I have 2 partial derivatives, dou f by dou x, dou f by dou y, and I have dx and dy. And I'm keeping it simple here. Just think of it as the same learning rate. Dx is negative 0.01, dy is negative 0.01. Okay. And I do the same thing. I calculate f, I calculate actual, and then I do an error. Okay. And I do 100 iterations, I get negative 2.44. Okay. Then I do something similar where I do 1000, just give me a moment. So in this case, same example, but 1000 iterations, much lower in terms of error. Now we know where we are heading, which we haven't touched upon. We'll do that in the next session, and we'll close our session on calculus with that, which is, sorry, it's not univariate, this is bivariate. Can we do a second order in the partial derivative world? Just as we did the second order derivative, the Taylor's approximation in the univariate world, can we do the second order in the bivariate world and get a better approximation? Yes, we can. And that is where what is called as Hessian matrix will be useful. That's where Hessian matrix comes into picture. I don't want to saddle you with this for the moment because there's a lot of information that I've already dumped. There isn't much beyond this. There is just Hessian matrix. I'll take you through an example. And then in the next session, I'll take you through the chain rule. Just as we saw the chain rule in the univariate world, we'll look at chain rule in the multivariate world, and then we'll stop with that. Okay. Any questions?
We see one question. So when we say about partial derivative, right? So it is like differentiating with respect to x or y. For example, you have two variables. Or if you take three variables, again, it will be one is, no, we are differentiating with one and other two is kept constant.
That is right. Correct.
So, so this is applicable only when all the three are not, if any of, assume that two variables are related. In that case also,
that doesn't really matter.
Okay.
You have a very valid point. If they're related, then okay, then you can actually use the chain rule. That's why chain, if you know that they are related, and if you can define a function, then you will use the chain rule. This is an example where I'm not going to go through the details, but take this case. X equal to some g of t, y is equal to h of t, and z is equal to f of x comma y. So here, look at this. Z is a function of x comma y. Okay. Yeah. So if you forget everything else, just focus on this. You might think x and y are independent, right? But the reality is apparently x is a function of t and y is also a function of t. They're not independent. They're all related. So that's why chain rule comes into picture. When all these things are related and then you have the relationship available with you, how do you calculate partial derivatives and what sort of partial derivatives can you calculate? That's why chain rule comes into picture. Okay. But yeah, the reality is you may not even know that there is a relationship. That is also there. If somebody just gave you this z equal to f of x comma y, and nobody tells you about x is actually g of t and y is h of t, then you wouldn't even know. You would just go ahead and compute partial derivatives the way you would usually do it. Okay.
Yeah, thanks.
But that's a very valid question. We'll come to that when we do chain rule. Anything else, folks? Nothing at all? Too heavy?
We see.
Mm-hmm.
I couldn't understand how the gradient vector is tangential instead of being normal.
Again, it's tangential to that curve, right? So when we say tangential, look at this. Isn't this tangential to that curve? Take this case. Isn't this tangential to that curve? It is, right?
But the gradient vector is combination of both of them, right?
The gradient vector is actually, okay, you have a valid point. So this is one component of the gradient vector, correct? This is another component of the gradient vector. So
Yes,
you're
yes.
right. The gradient vector is a combination of both this and this. And these two are normal to each other, correct? You can see that, right? Don't you see that? This angle is 90 degree.
Yes, we see.
That is true. Gradient vectors are normal to each other. There's no doubt about it. I mean, when I say gradient vectors are normal to each other, I mean the components of the gradient vector are normal to each other. Don't you see that? So think of this as one component of the gradient vector. This is another component of the gradient vector. And of course, this angle is 90 degree.
But here, two components, they are there, so they point to two different directions.
That's right. They point to two different directions.
Take that vector, the vector will be pointing into only one direction, right? Like combination of these two, it will be pointing to
Okay. Yeah, you're right. You're
someone.
right. You can do that always, right? When you have vectors, when you have the components of two vectors, you can figure out. But again, let me put it this way. Don't get bogged down by that. I'll tell you why. Because when things are in 3 dimension, you can do all this imagination. Okay. But when you move to say 4 dimensions, you can't even imagine how it will look. So don't be particularly bothered about the combination of these two components, how will it look and all that. We know that dou f by dou x and dou f by dou y can be represented. So that when we use the term gradient, we mean both dou f by dou x and dou f by dou y. Okay, both put together is a gradient. Can we imagine that as a vector? Yes, we can imagine that as a vector. What are the components of that vector? Dou f by dou x is one component. Dou f by dou y is another component. And you can imagine both of them as tangents to different curves in this particular case that we already saw. Are these components perpendicular to each other? Yes, of course, they're perpendicular to each other. That's it, nothing more. So don't go beyond that.
Okay, I see.
Anything else? All right, if there isn't anything else, let's stop for the day and we shall continue on Monday. Have a good weekend, folks. Bye.
Thank you. Bye.
Have a good